So we're seeing Alice, the mid station, and Bob in our visualization. And then as expected, we see that both nodes apply certain operations to their local qubits, and they achieve local entanglement between them. And then they both send a qubit to the mid station over the fiber. And the mid station receives the qubits here. We're seeing that it received the qubits, and then it is applying the Bell state measurement. And then the results from that measurement are being sent back to Alice and Bob, as we see here in this blue lines. And then here we've got a message saying that the protocol failed in the round 1, meaning that we didn't get any detections in the beam splitter detector. So we're gonna have to scroll down a little bit more to understand, to see what else happened in the simulation and see if we were able to achieve end-to-end, entanglement between Alice and Bob. So let's scroll down a little bit. We see how the protocol started all over again because it failed in the first round as expected, but then we see that it fails again. And then, it starts and keeps failing, Mike. So this doesn't look too good.
Not too promising at all. Well, that's unfortunate. Are there, one of the things that looks like it is happening in the transmission, and I'm wondering, again, not being an expert here, but just looking at the visualization, if it's something having to do with the photon loss, which is really critical. It reminds me a lot of, in classical networking, you'd have something called packet loss, which is due to losing too many bits along the line and not being able to get a full packet through as a result of that. In this case, the photon loss is creating qubit loss, it looks like. And I'm wondering if, we've got the parameters from the telco for the fiber optic lines that we're using. I wonder if maybe something along the lines of maybe the attenuation is too high. Maybe maybe it's being caused by crosstalk on the fiber optic cables that are in there, or maybe something else is being transmitted over that fiber optic cable that the carrier maybe didn't realize, or maybe the way it's mounted, maybe it's above ground, maybe it's below ground, and there's some interference happening there. Is it possible for us to go back to the telco and say, hey, we ran the model, we used your numbers, your parameters, and we can't even get the network to really work at all. We're not getting the establishment here from end to end of entanglement. Can you take a look at maybe passive components, crosstalk, and repairs, and maybe where the cables are mounted? Could that be something that they would look at and then maybe come back to us with an assessment and maybe some better numbers for us?
Yes, definitely. That's the process we're going to be probably doing to actually take new parameters, because the previous parameters that we used are not too promising. So we're going to take new parameters this time, and then we're going to see if that improves our simulation. So you're right, this is likely due to the attenuation in the fiber. And actually, if we look at the attenuation coefficient that we used, 20 decibels per kilometer is actually a lot. So this might mean that the fibers, there's something wrong with the fibers, definitely. So let's say that we are now simulating, optical fiber cables that are in better conditions. So let's, change this to a more standard value for fiber optic cables. So let's say that now we're going to be experiencing 0.2 decibel loss per kilometer. And okay, let's see how that improves our simulation this time.
So this is even something we could go back to the carrier and say, this is our minimum threshold that we absolutely need to have for an entanglement-based network to actually be viable, and give them that benchmark that they have to meet, and let them go figure out what passive components, what crosstalk, what attenuation is causing issues that isn't able for them to meet that criteria.
Exactly. Okay, we're all set. And then let's take a look again at what we got this time with this new fiber parameters. So, same procedure as before. The nodes are performing the protocol, and then we continue to see some failures in the in the protocol. But then, we scroll a little bit down, we see that it finally was able to complete here, right? So it started, the process after failing, but then it completed the round 1, and we're expecting then to see the protocol go over to the round 2. And this is what we're seeing. Now, Alice and Bob again perform an operation to their local qubits. They send one back to the mid station. But yeah, here we got that the second round failed. So still, we have to repeat the protocol. So why don't we go and try to find where this simulation was actually successful. So a little bit further down in the simulation, we finally see that our protocol has completely succeeded, and we have achieved entanglement between Alice and Bob.
Okay, Michelle, that's fantastic. This is good. That looks normal. But I have to tell you that, I'm looking down here in the visualization, and I see a fidelity of 0.65, both at Alice's location and at Bob's location. And I know already that if I'm going to carry keys across this infrastructure, I can't have a fidelity of 0.65. I want to have something higher than that, I think. What is it that could be causing this? I know you talked about visibility, and I'm kind of wondering if could there be a timing issue, between Alice and Bob, maybe how often the photons are arriving, or maybe the timing of the photons. Could that be causing this fidelity issue at both Alice and Bob's location? There.
Yeah, so that's a great observation, Mike. Definitely, the more our photons tend to be indistinguishable, then the higher the fidelity we're going to get on the entanglement. So we said for the previous simulation that we were going to have a 0.3 probability for the visibility, and that seems to be really low, and we're not getting the results that we're expecting. So we're going to have to change that to a better probability if we want to have better results.
So maybe in our system, the way in which we provide synchronization, maybe we need to select a better methodology for that, or a better components, whatever it might be. So we go back, we take an analysis, look at that, we bump up to this better timing system, across the entire network, and then implement that, and then so you'll model this kind of improved model that we'd be looking at to achieve.
Yes, exactly, Mike. That's right. So